Thank you for the introduction. So as Mel Nathanson mentioned, my name's Olivine Silier, and why? Okay, great. My name's Olivine Silier, and last summer I worked with my mentor, Prof. Adam Shepard, on structures of point line incidences, or another way of naming this is structural Trotter theorem type incidence structures. So before I start, I'd like to first thank the the Lynn A. Booth and Kent Cressa Sir Fellowship that funded this research. So just a brief roadmap to show you the adventure that we're going to be following today. So I'm first going to give you an introduction on point line incidences, what they are and what is known up to now. And then we're going to talk about why we care about these things. And then we're going to segue into our last summer's results with first a family of configurations that we found that have these interesting properties we seek, and the structural result that is very interesting. But so in the spirit of making this light talk, more, accessible and less of a math strain for all, we're going to just introduce this main simplification, which is that in this talk, all the results and the constructions will assume that the number of points and number of lines we are considering are the same, and we're just going to call this number n. And also, this is more due to the nature of the results and where the field is at currently. Most of the point sets that we'll be considering will be Cartesian products. More specifically, most of them will actually even be lattices. So you can just picture this to be grids, like regular grids. Okay, so first of all, a point line incidence is defined, as you see here, as a point line couple such that the point is on the line. So it's a standard definition for any geometric incidences. And so here I have some examples for those of you who are not as familiar with this definition to kind of see what we're talking about. So here we're always talking about incidences between lines and points in R2, so just the plane. And so in the first example we have 0 incidences because, well, the point is not on the line. And then in the second case, we have 1 incidence because we have 1 point and 1 line that form an incidence together. The second one is 2 because we have 2 couples. And then the last example, we have 6 for the same reason. So what the state of the field at this point is that we have this very famous, very important similarity Trotter theorem that many people yesterday and today have mentioned in their talks that I also saw in combinatorics class last year. So a very foundational theorem, which in this specific case, where we have a few simplifications, we assume that the point set and the line set contain the same number of elements. And then this theorem states that the number of incidences, so I of PL, is going to be at most the n to the 4/3. So that's what this big O notation means. If you're not familiar with it, it's just asymptotic notation. That means that if you assume that n is large enough, then up to constants, this bound holds, right? And so the thing to note is that we have an upper bound here, and we don't really care about the lower bound because it is trivial. And this is just because you could always pick points that are not on the lines, like the first example I gave, in which case you would just have 0 incidences, at least in this context. The other main results to note is that 2 extremal constructions, that is constructions that actually meet this upper bound, are known, and that means that the Summeretti-Trotter theorem is tight. It means you can actually construct like points and lines that will reach this upper bound, and therefore you can't do better than this Summeretti-Trotter upper bound. And so these are sort of old constructions, one by Erdős and the other by Ellicott, but not much more than this is known, at least in the construction department, because for example, no constructions were known where the point set is not like a lattice. Okay, so our results kind of mirror this dichotomy between structural theorem and construction that then matches the upper bound from below. So our structural theorem, or at least this is the main result that I'm going to be presenting today, says that if you are in the case where you have this maximal number of incidences, written here in asymptotic notation, then you're in one of two cases. Either you have many families of many parallel lines, or you have many families of many concurrent lines. So what that means is if you are to have a construction in R2 on the plane with lines and points that are such that you have the maximum number of incidences, so you maximize the number of incidences, then either you're going to have a bunch of subsets of this line set that are all parallel together, or you're going to have a bunch of subsets of the lines that all intersect in a given point. And then our constructions result is a generalization of the Erdős and Ellicott constructions mentioned earlier, which gives a solution, at least in the case where the line set and point set are the same size, for all choices of formats. So like all shapes, possible shapes of the line set. That means it's like parameterized by the size, the number of x coordinates versus the number of y coordinates. Okay, and so right now, before we delve more into that, I'm going to talk about why we care. And so as many of you are aware, because this is, we're all mathematicians here, these point line incidences results and incidences more generally have applications in all of these fields, because, well, through the guise of, for example, additive combinatorics, you can have some equivalences between like incidences, number of incidences and other mathematical tools. So it's useful, but it's also interesting in a more fundamental and just curious way, because another well-known examples of incidences that have a strong relationship with the underlying geometry of the problem is, for example, the unit distances problem, which is another incidence problem in which we care about a set of points and we want to maximize, or we want to search for the maximum number of couples, point couples that are at a unit distance from each other. And it so happens that this bound on this unit distance problem varies wildly with the norm that is chosen. And in fact, if you take, for example, the L1 norm or the L infinity norm, it's kind of a trivial thing. But if you look at the standard, like, Euclidean like L2 norm, then this is an open problem that's very interesting and tricky. Right, and so to thank you for waiting till the end of the day to listen to this talk, I'm also going to introduce some jokes, and here's the first one. It's more of a pun. So why did the line give up? Because there was no point. Okay, moving on. So here I'm going to build up some intuition for explaining the constraints and the issues in trying to construct a point line structure that actually has this maximum number of incidences. And so we're going to start with a toy problem, where if we start with a Cartesian product point set, which is the type of point set in which we have the most results or the most understanding. Specifically, if we choose it to be a lattice of points, let's just fix some numbers so we can visualize this. Here we're working with a 5 by 125 lattice of points, and I have a few questions for you. Sorry, 5 by 25. So what is the maximum number of these points that you can get on a single straight line? And the answer to this is 25, and that's just because you can't do better than just put a horizontal line that is on this maximum direction. And if you were to exclude the horizontal line case, the best you can do is 5, because you can get at most 1 point from each row. Right, so like with this in mind, you can try to generalize this a bit and see where things start breaking down. So right now, let's assume we're in a Cartesian product point set case where we have n to the 4/3 many points, like many x coordinate options, and n to the 1/4 many y coordinate options. So it's even more squished than before. Then again, by the same reasoning, the maximum number of points on a line is going to be n to the 3/4 if you are in a horizontal line case. And if you're excluding the horizontal line case, you can do at most n to the 1/4 points on a line, because you can have at most 1 point from each row. So then counting the number of incidences, total number of incidences, you can get at most n incidences from the horizontal lines, because you have only n to the 1/4 rows. And then from the non-horizontal lines, you can get at most n to the 5/4 incidences, because you have at most n lines, because we're still assuming that we have n points and n lines. The reason why this is interesting, or the bottom line, haha, is that n to the 5/4 is smaller than the Trotter upper bound, which is n to the 4/3. And so what this tells us is that if your point set is like too squished along one direction or the other, you can never actually reach this like Trotter upper bound. So stating this a bit more formally, if you are in the case where your point set is a lattice, or more generally a Cartesian product, parameterized by this alpha here that tells you like how many x coordinates, how many y coordinates you have in your lattice, then if you want to have this maximum number of incidences corresponding to the Trotter upper bound, then you need your alpha parameter to be within this range. And it's exactly the same reasoning as what we showed before, just done a bit more rigorously and generally. And the Elekesh construction actually corresponds to the case where alpha is 1/3 and the Erdős construction to alpha is 1/2. And what we did is, by combining these two strategies, I guess, and generalizing a bit, we actually reach this family of constructions that gives you a construction where you can have a point set with any alpha within this allowable range, which is very exciting. It means that we actually are able to reach all of the possibilities for the case where the point set is a Cartesian product. Right. Okay, so let's take a break. Here's another pun. Why was the impatient point reluctant to be in an incidence? Because it didn't want to get in line. Okay. So here's the last part of my talk, and it's about the structural result that we found. And it is stated here. I'm just going to put it out there and give you a second to look at it. So what it says is, if you are in the case where your point set is a Cartesian product, and you are also in the case where you have the maximum number of point line incidences, note that we're still right now assuming that the number of lines is equal to n as well, then you must be in one of two cases. Either there are many families that each contain many parallel lines, or there are many families that each contain many concurrent lines. So this is a bit more rigorous statement of what we had before in the introduction. So you will note that these parameters have a certain range, and the certain range depends on the shape of the Cartesian product. And so it means that, unfortunately, for example, as alpha gets larger, this range becomes less and less strict. Right. Anyway, but then if alpha is very large, then you have a very large constraint, which is very interesting from a structural point of view. Right, so I'm just going to walk you through two of the, or I guess just the big ideas behind this proof, because it's kind of fun and interesting, so that you can kind of see where this comes from. So the first thing I need to introduce is this concept of point line duality. So the idea is, if you have a point in R2, you can just write it as like the point AB, X coordinate, Y coordinate. And then any line L in R2 will also be expressed in terms of two parameters A, B, where here your line is the line Y is equal to AX minus B, which means that you can also express L as a two tuple, which means that you have this way of swapping between points and lines. So we're going to use this trick to be able to look at lines as functions and therefore points also as functions, which means that we can now do this nifty thing, which is define point energy. And this is going to be noted as E of P, where P is your point set, or equivalently your line set. And this is just going to be the number of four tuples in the point set you're considering, such that this is true. And here, notice that we're using composition, like function composition, on these points, and that is possible because now we can consider points as functions, as linear functions, through this point line duality. This seems to be kind of random and far-fetched at first, but this definition is motivated by other tools in like additive combinatorics, where you'll see sort of similar definitions for example, additive or multiplicative energy. And this is a relatively recent notation, but as you will see later, it actually comes in very handy because it allows you to parameterize your point sets in an effective way. The last thing I will say about this is point line duality is very interesting because if you are working with a point line construction and you go to the dual, which means you swap points and lines, you actually conserve the number of incidences in the structure, which is also another motivation for doing this, defining this equivalence. And so the second point here is that using this definition of point energy bound, of point line energy, we found this result here that is allowing you to bound the point or line energy if your point set or line set is a Cartesian product, written here as A cross B, in terms of a product of the multiplicative additive energy of the like X coordinates and Y coordinates. And the reason why this is useful is because we can then plug this into this recent result by Rudnev and Shkretov, which allows you to find an upper bound for the number of incidences between a point set that is a Cartesian product and a line set in function of the dimensions of the Cartesian product and the line energy that you're working with. Recall that you can map from points to lines and vice versa. So actually this point energy and line energy are the same object. And so then using these two results together and using like dyadic decomposition and tricks, we can then find this. And the, I guess, overall idea here is that if you have a certain understanding of the dimensions of the Cartesian product you're working with, you can then quantify and split like x coordinates and y coordinates both through this bound and this bound, which will then allow you to double count the number of incidences in terms of the structure of your set. Okay, so I want to just end on a high note, hopefully, through this joke. So when not too recently, I was doing some like math Olympiad stuff. I had lots of painful moments when at the end of trying to draw out this complicated, geometry question structure, I would end up on the last line of the question that says something like, the 3 lines that you drew earlier intersect in a point T, except my 3 lines look like this. And so at least in French math Olympiad camps, this is a common issue. And what we all did is this, which is you grow exasperated and just draw a huge dot in the middle and call it T. And this gave rise to the fundamental theorem of geometry, at least according to us, which is any 3 lines will intersect at a single point if the point is large enough. That's all for me. Thank you very much for listening. And I'm not quite sure how much time we have, but I'll.
Oh, thank you very much.